This is a physics video, and I'm following Young and Freedman's University Physics. We are almost done with chapter 21, just this video and one more. This video is on electric field lines. So an electric field line is an imaginary line or curve drawn. So like here's an imaginary curve. There's nothing there, right? I mean, you can actually, they show a picture of kind of putting seeds, to show how the seeds line up with these imaginary field lines with a magnetic field, a charged field, I think, actually. But an electric field line, like this curve here, is an imaginary line or curve drawn through a region of space so that it's tangent. So these are tangents, tangent of the field at point P, tangent of the field at point R, so that its tangent at any point is in the direction of the electric field vector at that point. Now you notice that the vector changes, with, for example, a curved field line. Michael Faraday is the one who came up with this. We're going to get to Faraday eventually, Faraday's law, one of the four great laws of electromagnetism. We've already had one of them, Coulomb's law, earlier in this chapter, and we're going to get the next one, Gauss's law, in the next chapter. But anyway, Faraday lived in the early 1800s, or did most of his work in the early 1800s, and he suggested, I think he called them lines of force. He didn't call them electric field lines. But anyway, we call them electric field lines. And they are imaginary lines that relate to the way that the electric field is progressing through space. And the direction of the field at any one point is the tangent to that line. Now you may ask, as I did, well, why would these lines of electric field, why would they curve? And the reason is they curve because of their interaction with other electric forces, electric charges. So it's the interaction of charges that causes them to curve. They would be completely straight, if, as we'll see in a second, if you only had one point charge. But when they begin to interact with other charges, then they begin to curve. And so an electric field line is an imaginary line or curve drawn through a region of space such that its tangent at any point is in the direction, gives us the direction of the electric field vector at that point. Okay, some characteristics of electric field lines. They show the direction of the electric field at that point. I think I just said that. Their spacing in diagrams indicate magnitude. So as we'll see in these diagrams at the end of this video, like if let's say you have a dipole where there are equal and opposite charges, right in between the charges is going to be a higher magnitude of the electric field than, say, way up here. And in the same way, let's say that they're of opposite charges, then they're going to repel each other, and the repulsion is going to be greater right in between, than out here. So the way that we draw that in these electric field diagrams, we draw the lines closer together to indicate a higher magnitude of the field. And it follows from what I'm saying that they can have different magnitudes at different points, and they never intersect. Okay, electric field lines never intersect. Now the convention is that these field lines, and I've said this in previous videos, that if you have what we've defined as a positive charge, then the field lines go away from the positive charge. If you have what we've defined as a negative charge, then the field lines go toward the negative charge. Okay, so let me end this video with some diagrams. They are hand drawn, so I'm trying not to, violate copyright or that sort of thing. So this is not, forgive my hand drawings. I think it might actually make this more real. These are, man, those Ken Schenk videos are so real. Anyway, so let's say you just have one point, then you have, again, straight lines of force in the case of a positive charge going away from the charge. Then these are called field maps, by the way. But if you have a dipole, again, I'm sorry, this is a horrible, what is it? It looks like a frog or something. It's a Star Wars character. Again, the field lines go out of the positive, that's supposed to be a plus, and into the negative, that's the way we're talking about it. Notice that the lines in between are drawn closer together to indicate a higher magnitude of the field than, say, out here. And again, these, these should be parabolas, not my kind of cone head, things here. They should be perfect parabolas because God likes perfection. So this is called a dipole, where you have equal and opposite charges. The final section of this chapter talks a little bit more about electric dipoles. Then lastly, if let's say that they are of the same charge, then you're going to get repulsion. Again, see the book. This is a reason to pay lots of money to get the actual textbook so that you can get actually professionally produced diagrams, okay? But basically, we have repulsion of like charges, and the field lines, again, higher magnitude in here, but they repulse each other. Well, this has been a video on electric field lines. And as physics videos go, I think it's been pretty painless. So have a nice day.